Hello students, good evening. Welcome to this video session of the discussion on the solutions for the heat transfer test which was conducted about 2 weeks ago. Okay, you might have written the test, you might have given the heat transfer test for the gate prepared during the gate preparation. Now I am going to discuss about the solutions pertaining to the heat transfer exam what you have written. In fact, this is a very important subject in the gate point of view. The weightage will be, you must have seen for the last 3 or 4 years, the average weightage is around 10 marks out of the 100. So, don't take it lightly regarding the preparation of heat transfer. It is a very important subject, slightly tougher subject as compared to the other. But if you prepare well, definitely you could score all the 10 marks if you prepare strategically, okay, taking all my videos and if you prepare a short notes and take the clues from my videos, definitely you would be able to bag all the 10 marks from this heat transfer subject. Come on, let us discuss, let me discuss about the solutions of this heat transfer exam questions which are written earlier, about 2 weeks ago. The question goes like this. This question is on the convection, because there are 4 chapters: conduction, convection, radiation and heat exchangers. The weightage will be among all the 4 chapters, weightage will be shared equally, but slightly more in the conduction, because conduction is slightly a bigger chapter. But generally all the students will feel tougher regarding the convection, but if you prepare strategically, the convection is the easiest chapter, because when you are discussing about the convection questions of the heat transfer, first of all we have to decide whether it is a free convection or a forced convection. Most of the questions asked in the gate, mostly above 90% of the convection questions will be from the forced convection, where you will be definitely given some velocity for the fluid. How do you decide it is a forced convection? Whenever there is a fluid moving on a body, whenever there is a cold fluid moving on a hot solid body, definitely there will be a forced convection heat transfer expected. This is a question on the forced convection heat transfer. Atmospheric air flows inside a 21 mm diameter tube. This is a 21 mm diameter tube. Air is flowing. D is the diameter, right? This is the air flowing with a velocity of 0.21 meters per second. Velocity is given in any convection problem, means it must be a forced convection problem. Heating can be done by condensing the steam. Is condensing the steam on the outside of on the outer surface. When the steam is condensing, definitely the temperature of the pipe all along the pipe, it will be constant. Definitely I can say it is a constant pipe wall temperature conditions. Okay, it is a constant pipe wall temperatures. How do I decide? Because steam is condensing. When the steam is condensing, its temperature remains constant, because any phase change from vapor to liquid or liquid to vapor, it is an isothermal process. Therefore, the steam is condensing outside, therefore the temperature of the wall all along the length of the pipe is constant. That much we can decide from that word, steam is condensing. Thus maintaining uniform, see, he has given certain uniform surface temperature. All along the length of the pipe, temperature is same. Properties of air were given. If the flow is hydrodynamically and thermally developed, the heat transfer coefficient at the pipe surface is, okay, fine. And whenever we are dealing with a forced convection heat transfer, we have to decide first whether it is an internal flow or external flow. Clearly it is an internal flow. Internal flow, that means flow through a pipes or the ducts. That is the first thing we have to take care whenever we are dealing with a forced convection. But is an internal flow or external flow, decided. Yes, it is an internal flow. Then what is the first step in any forced convection heat transfer? We have to calculate the Reynolds number. By calculating the Reynolds number, you will be able to decide whether the flow is laminar or turbulent. Laminar or turbulent. So based on that particular distinction, if I have to calculate the Reynolds number, decide whether the flow is laminar or turbulent, and based on that kind of flow, we have to select the formula for calculating the convection heat transfer coefficient, because the convection heat transfer coefficient H will be calculated from the relation among Nusselt number, Reynolds number and Prandtl number. Reynolds number and Prandtl number. Okay. So, by calculating this Reynolds number, you will be able to decide whether the flow is laminar or turbulent. First, let me calculate what is the Reynolds number here. Reynolds number will be, formula is Vd rho by mu, which can also be given by Vd divided by nu, where V is the mean velocity of flow, D is the diameter, nu is the kinematic viscosity. They were given. You see, the kinematic viscosity velocity is how much? Velocity is given as 0.21. Diameter is 21 mm diameter, but we have to convert into the meters. All the dimensions must be kept only in meters. Kinematic viscosity is given as 20.76 into 10 power minus 6. That is the kinematic viscosity. This nu is called kinematic viscosity, having the units of meter square per second in the SI system. So, this is the Reynolds number. I got the answer, Reynolds number, as 212.43. Yes. Now, based on this, Reynolds number is a dimensionless number defined between the inertia forces and the viscous forces. We have calculated the Reynolds number, and how to decide whether the flow is laminar or turbulent. As long as the Reynolds number is less than 2000 for internal flows, as long as the Reynolds number is less than 2000, the flow is laminar. If the Reynolds number is more than 4000, flow will be turbulent. Clearly, it is definitely lesser than, much lesser than 2000. Therefore, I decide the flow as laminar flow or viscous flow. Other name of laminar flow is viscous flow. For the laminar flow, how to calculate the H? But because our main unknown is the convection heat transfer coefficient, H. How to calculate the H? See, once the flow is laminar, it is a constant wall temperature conditions. When the flow is laminar for internal flows, there are two situations may arise: constant heat flux conditions and constant wall temperature conditions. Two different situations they may arise. Now, here the situation is constant wall temperature conditions, constant pipe wall temperature conditions, right? So, for this is our situation. Now, this is our situation, constant wall temperature. For constant wall temperature conditions, Nusselt number is given by Hd by K is equal to 3.66. Had it been a constant pipe wall temperature conditions, Nusselt number formula will be Nu is equal to 4.36. So, the value for the Nusselt number will be different for the constant pipe wall temperature conditions and different for the constant heat flux conditions. How do you decide it is a constant pipe wall temperature conditions? Because he has given the word steam is condensing. When steam is condensing, it is an isothermal phenomenon. Therefore, pipe wall temperature is maintained constant all along its length. So, this is the situation we have decided. Therefore, Nusselt number formula is given 3.66. For internal flows, mind that only all this discussion is regarding the internal flows. If the flow is external, like a flow over a flat plate, the formula for the Nusselt number will be different, entirely different, right? So, we require the H value. Diameter is given, thermal conductivity of air is also given. Therefore, H into, what is the diameter? 21 into 10 power minus 3 divided by thermal conductivity of the air is given as, for your information, air is a very poor conductor, very bad conductor of heat. Its value is just 0.03, okay. So, is equal to 3.66, from which H can be obtained as, answer is 5.2 watt per meter square Kelvin. This is the answer, okay. So, this is the algorithm for particularly, though people feel that convection problems are a bit tough as compared to the other chapters. In fact, if you follow the algorithm clearly, the sequence, how to calculate the H value properly in convection, there is a procedure, certain procedure. What is the procedure I want to tell here is, first decide whether a flow is internal or external, number one. Once you decide the type of flow, then whether it is a forced convection heat transfer. If it is a forced convection heat transfer, decide, first calculate the Reynolds number, decide whether the flow is laminar or turbulent. Supposing if the flow is turbulent here instead of laminar, I would use that Dittus-Boelter equation, which is also called as the Macadam's equation. Nusselt number is equal to 0.023 into Ru to the power of 0.8 Pr to the power of N. Okay, that formula is meant for the Reynolds, for the turbulent flow if the Reynolds number had been more than 4000. Okay, if the flow is laminar, you have two different situations, constant heat flux and constant wall temperature conditions. Okay, because it is a constant wall temperature conditions, Nusselt number is 3.66. Supposing if it is a constant heat flux, then the Nusselt number will be 4.36. Please remember 48 by 11 or 4.36 if it is a constant heat flux. But generally, if it is a constant heat flux conditions, the situation will be different. There will be an electrical wire or cable will be wound all around the length of the pipe. Generally, if it is a constant, I repeat once again, if it is a constant heat flux situation, then the arrangement of heating will be different. It is not the steam condensing, rather it will be an electrical wire or the cable wound around all along the length of the pipe. Then the constant heat flux conditions will be maintained, then the Nusselt number will be 4.36. But here it is a constant wall temperature conditions, Nusselt number will be 3.66. That is the answer. Fine. This is a question. You have answer, got the answer as 5.2 watt per meter square Kelvin. Right. This is the second question goes like this. A solid sphere of radius. There is a solid sphere of radius 0.6 meters. Radius has been given. There is internal heat generation Q dot. Generally, internal heat generation is denoted by Q dot. At the rate of what is been Q dot given 5 into 10 power 4 watt per meter cube. This is the symbol, generally we use it for the heat generation. Heat will be generated by passing electric current or chemical reaction, whatever the means it may be. There is an uniform internal heat generation throughout the sphere. It is a sphere of radius R. R value has been given. What is the R value? 0.6 meters. If the thermal conductivity of the material is 7.72 watt per meter Kelvin and the temperature at the outer surface of the sphere is here TW, outer surface of the sphere is 95 degrees Celsius, the temperature at the center is asking, the temperature at the center at this location T naught. T naught is the center temperature at the center, TW will be the peripheral temperature or the surface temperature. Under steady state conditions, definitely all the heat generated inside the sphere might be transferred by convection, H watt per meter square Kelvin. To maintain the steady state, remember, whenever there is a heat generation in any body, maybe sphere or a cylinder or a slab, if you want to maintain the steady state conditions, all the heat generated in the entire body must be convected from the surface of the body to the fluid. I repeat once again, if you want to maintain the steady state conditions while generating heat inside a body, if you want to maintain the steady state conditions, entire heat generated, let's say for example 100 watts you are generating, that means 100 joules of heat is generated in 1 second. In the same 1 second, all that 100 joules of heat must be convected from the surface of the body to the fluid, convection to the fluid. Then only that steady state conditions can be maintained. Otherwise, we cannot maintain steady state. Mostly 99.99% we will assume that conditions are steady. Then under that conditions, what is the central line temperature is asking. Under steady state, what do you mean by steady state? First of all, the temperature of the body at any particular location will not change with respect to the time. Under steady state for sphere, T naught will be the T max, T naught minus TW is equal to Q dot R square by 6K. This is the formula, please remember. If it is a cylinder, it will be 4K. If it is a sphere, it will be 6K. T naught is the maximum temperature which you see at the central line temperature. Q dot given, K is given, K, what is the K value given? 72 watt per meter Kelvin. K has been given. R is given as 0.6 meter. Radius of the sphere is been given. Q dot given. Q dot you have written here 5 into 10 power 4. TW is also given. Okay. So if you substitute T max, the maximum temperature that is at the center will be 136.66 degrees Celsius, or you can round it up to 137. Okay. Generally, in the gate examination, don't round it up. Don't round the answer. Generally, he will expect you to answer, particularly in the gate, in the fill in the blanks, numerical data type, NDT questions they are called. Don't round it up. After decimal, minimum 2 digits you have to type the answer correctly, then only you will be given a full marks. Okay. If you round it up, you will be getting a 0 mark. Don't round it up. After decimal, 2 digits you have to correctly type in the gate answer system, right? And had it been a cylinder, first of all I would like to tell you that if it is a cylinder, cylindrical body generating the heat, then again the maximum temperature will be seen at the axis. Then again the maximum temperature will be seen at the axis here. At this location we see the maximum temperature. Minimum temperature will be at the surface, peripheral temperature. But here T naught, T max minus TW or T naught we can also say. It will be Q dot R square by 4K if it is a cylindrical body. Now what we are given here is a sphere. Answer is 136.66. Let us go to the next question. Any doubts? Please try to type it. I can chart here. Please. If you want to have any doubts, please you may chart right now. I could clear your doubts. Okay. I could clear your doubts. If you have any things, you may type and send me right now. I would be able to answer at once right now. Okay. Let me go to the third question. Don't hesitate to answer the doubts. If you are asking the doubts, means I would feel very happy to clear your doubts, because if you are getting the doubts, it is a sign of your understanding the subject. Getting the doubts is a perfect sign of you are understanding the subject. Okay. The third question goes like this. A 2.5 mm diameter electric wire is covered with a certain thick layer of insulation. There is a wire. Okay. On that there is an insulation packed. Insulation thermal conductivity has been given 0.6 watt per meter Kelvin. Okay. This is the wire. Air surrounding, this is the air surrounding temperature is 27. This is insulation, all this is insulation. From the surface of the insulation, there is a convection mode of heat transfer happening. Convection with H value is 20 watt per meter square Kelvin from the surface of the insulation, right? A wire has been surrounded by an insulation. Okay, the maximum value of heat dissipation from the wire will be, when will you expect there is a maximum amount of the heat transfer from the wire to the atmospheric air? If this is a wire, this is insulation, right? This is insulation. All this is the insulation. All this is the insulation. So when you will expect the maximum heat transfer from the wire? This is a concept of the critical radius, right? This is a concept of critical radius. When you provide the critical radius of insulation, which is given by the formula K by H, then under that condition heat transfer rate will be maximum. You can expect the maximum heat transfer rate from the wire to the air. There is air here. You may expect the maximum heat transfer rate only when you provide the critical radius of insulation. So first let me calculate what is this critical radius of insulation. What is the formula for the critical radius of insulation? K by H. K is the conductivity of the insulation, not that of the wire. Mind that K is the thermal conductivity of the insulation. First let me calculate what is that critical radius of insulation. It's a very important concept in conduction chapter. 0.6 divided by H will be 20. 0.6 divided by 20. That is a critical radius of insulation. Let me check how much answer I got. It is a 0.3 meters, 30 mm. Okay. This is the, then under that condition, what is the, suppose that means if this is the radius R1, what is the radius of the wire? 2.5 mm diameter electric, that is 1.25 mm radius, that is the diameter. Now what is the critical radius we got? 0.3 meters, that is 30 mm. 30 mm. This is 30 mm critical radius. This is corresponding to where there is a maximum heat transfer rate. This will be critical radius happen to be 30 mm we got. Okay. Radius of the wire, original radius of the wire is 1.25. Now, between the, what is the surface temperature of the wire? 120. This is 120. Air temperature is 27. Between the wire and the air, how many resistances are there? One is conduction resistance followed by convection resistance. H value has been given. How much H value? 20. Okay. So, between the wire and the air, between the wire which is at a temperature of 120 and the air which is at a temperature of 27, how many thermal resistances are there? Two resistances. One is conduction resistance offered by the insulation. Second one is the convection resistance at the surface of the insulation. Mind that there are two resistances here between the wire and the air. One is conduction resistance offered by the insulation. Second thing is the convection resistance offered at the surface of the insulation. First, let me draw the thermal circuit. Thermal circuit is very important in the first chapter of that is called conduction. How many resistances are there? Two resistances. First one is conduction resistance. Second thing is the convection resistance. This is the conduction resistance offered by the insulation. This is the convection resistance which you are seeing at the surface of the insulation. So, what is the temperature here? Temperature of the wire has been given 120. One terminal we know. What is the temperature of the air here? 27. That is room temperature. What is the conduction resistance formula? Ln R2 by R1. What is the R2 value here? 30. R2 by R1. What is the radius of the R1 is what is the radius of the wire? 1.25 log R2 by R1 divided by 2 pi KL. What is the K value of the insulation? 0.6 into length. I think if not mentioned, take it per the 1 meter because already in the units also given. See that 1 meter length you can take it as 1 meter. In the case of the cylinders, if the length is not mentioned, you may feel free to take the for 1 meter length. Then what is the convection resistance? 1 upon HA. Okay, convection resistance is 1 upon HA. Conduction resistance is ln R2 by R1 divided by 2 pi KL. Length is not given, but I have taken it as a 1 meter. What is the 1 by HA convection resistance formula? What is that? 1 upon HA. What is the H value given? H value is 20. What is the area of convection? Area of convection will be, look at this, 2 pi R2L. That is at the surface of the insulation. What is 2 pi R2? R2 is 0.3 meters. This is a critical radius. 2 pi R2 will be 0.3. Length is not mentioned. You can take it as 1. Now you can get the Q max. How to calculate Q max? 120 minus 27 divided by sum of these two resistances. What are the two resistances? First one is the conduction resistance offered by the insulation. Second one is the convection resistance at the surface of the insulation. Q max answer will be 83.92. I am writing here. Q max will be 120 minus 27 divided by sum of the two resistances. Sum of the two resistances will be 83.92. That is answer. So, the concept here is because he has asked the maximum value of heat dissipation, heat transfer, that word itself tells that we need to calculate the critical radius of insulation. Critical radius of insulation concept is that for thin wires, if you wrap the insulation, for thin wires, if you wrap the insulation, it will result in the increase of heat transfer rate instead of decrease of heat transfer rate. Instead of decreasing the heat transfer rate, after putting the insulation, heat transfer rate will be more. Okay, that is the main concept regarding the critical radius. The heat transfer, as you keep putting more and more insulation, heat transfer also keeps on increasing, reaches a maximum and then decreases. So the maximum heat transfer rate you will see corresponding to the critical radius of insulation given by K by H. Right. So that is the answer for the third question. Let me go to the next question 4. I invite you for any doubt discussion. Please keep asking the doubts if you have any. Okay. See the doubts if you are seeing them. Okay, any doubts, you feel free to chat with me. Fourth question, lubricating oil enters a 2 centimeter diameter tube with a velocity of 4 meters per second. Tube wall is maintained at 30 degrees Celsius. Yes, it is a constant wall temperature because very clearly mentioned that it is an internal flow. It is an internal flow. The tube length required to cool the oil from 60 to the 45. Tube wall is maintained at 30 degrees Celsius. First, let me put it on a pictorial manner. There is a tube. There is a tube at which is maintained at a temperature of TW is 30. Heat transfer coefficient also has been given. Okay. The tube length required to cool the oil. Cool the oil is entering THI, I can take. It is 60. It is coming out at 45. How much length of the tube is required by maintaining a constant pipe wall conditions? It's a very good question. First, I take a differential control volume, a small differential length of the pipe I consider. For that I write the energy balance. There is a mass flow rate. Okay, mass flow rate of the oil. A differential control volume of length dx. Supposing if this is the x direction, dx I have considered. If dq is the differential heat transfer rate between the oil and the pipe for a length of dx, dq is differential heat transfer rate between a pipe length of dx, between oil and pipe length of dx. Then if dq is differential heat transfer rate between oil, there is an oil flowing like this. This is the mass flow rate of the oil. Then from energy balance, energy can neither be created nor destroyed. We have to account for the energy. Then from energy balance, dq is equal to minus m dot Cp dt. Okay, m dot Cp, that is a differential decrement in enthalpy of the oil for a travel of dx. That should be equal to what is the heat transfer rate? H has been given, pi dx into length, into temperature of the oil, right? Temperature of the oil minus 30 at that location. At that location, what is the temperature of the oil? Okay, m dot has been given. We can differentiate. You can integrate by separating the variables. Why I have written the minus there? Because the temperature of the oil, when the oil enters at certain temperature, dt will be the differential drop in temperature of the oil because of the differential heat transfer rate. If you separate that, minus m dot Cp, separate the variables, divided by T minus 30 is equal to H A delta H pi dx. Sorry, this length will not be there because H into pi d, diameter has been given, into dx. Area of heat transfer, see that. What is the area of heat transfer? Pi d into dx. This is the differential heat transfer area. As the oil passes through this differential control volume, what is the area of contact between the oil and the pipe length? For this differential length, pi d, d is the diameter, d is the diameter of the pipe, pi d into dx, that is the contact area or the convection area. Here the energy main point what you have to understand here is, what is the differential heat transfer rate between the oil and the pipe wall? What is the differential heat transfer rate between the oil and the pipe wall? That should be equal to the differential decrement in enthalpy of the oil given by this m dot Cp into dt. What is this dt? Differential drop, differentially small temperature drop of the oil as the oil travels a distance of dx. So for that distance of dx, what is the differential heat transfer area? Pi d. Convection area is always the contact area. Remember, according to the Newton's law of cooling of convection, the convection area is just nothing but the contact area between the solid and the fluid. What is the contact area there for the differential length? Pi d into dx. Okay, this is the Newton's law of convection, Newton's law of cooling. This is the energy balance for differential heat transfer rate. The decrement in enthalpy is given by minus m dot Cp dt. Why I have written this minus is, in the direction of x, the temperature of the oil will be decreasing because oil is losing the heat, right? Now you can pi d, h pi d into dx. Now you can integrate this. What are the limits for the temperature of the oil? You can temperature of the oil inlet is Thi will be 60, at the exit it will be 45. Now we can remove this minus and interchange the limits. It becomes m dot Cp log T minus 30, ln T minus 30 between the limits 60 to 45 degrees Celsius. H has given, pi has been given, pi is known. What is the diameter of the pipe? 2 centimeter diameter, 2 centimeter diameter there. 2 divided by 100 into length. H is known, everything is known. You can calculate the length of the tube. That velocity given, it is a superfluous data. I think if the m dot is not known, actually m dot is not given here actually, yeah. That is where this velocity has been given. This m dot is not given from, I have the continuity equation. What is the continuity equation? M dot is equal to rho into pi by rho AV, pi by 4 d square into velocity. Is the density of the oil given? Yes, given 870. Diameter of the pipe known, velocity of the flow of the oil is known. Here the m dot I got it as 1.0927 kg per second. Mass flow rate. This is continuity equation. Continuity equation you should not forget, because that is a conservation of mass. Continuity equation is used in thermodynamics, fluid mechanics, heat transfer, power plant. In so many subjects the continuity equation is used. What is the continuity equation? Mass flow rate is given by rho AV. M dot is given by rho AV. V is the velocity of flow. Diameter is known. Density of the oil is given. We get the mass flow rate. Substitute here. Substitute in this equation. And now we get the length of the pipe as 22.6 meters. Very good question this is. Very good question in convection heat transfer. So I would once again explain. There is an oil is losing the heat to the pipe. Oil is losing the heat to the pipe by convection. The differential heat transfer rate is differential drop in enthalpy of the oil. Differential heat transfer rate is differential drop in enthalpy of the oil. That is differential heat transfer rate is given by minus m dot Cp into d2. Differential enthalpy drop, differential enthalpy change of the oil because of the differential heat transfer rate. This is given by Newton's law of cooling. This equation is known as Newton's law of cooling. Convection, basic equation behind any convection. HA delta T. What is the T? T is the temperature of the oil. So Newton's law of cooling says that HA delta T. What is the delta T? Temperature difference between the oil and the surface of the pipe. Okay. Now T is the temperature of the oil at this location. I will mark it here. T is the temperature of the oil at that control volume of length dx. So very good question. Such kind of questions will be expected in the gate. Very good question this is. We have used the continuity equation, we have used the energy balance, separate the variables and integrate. That minus sign only says that as the in the direction of the x, the temperature of the oil is decreasing, because oil is losing the heat. Oil is losing the heat, that is why temperature of the oil is decreasing in the direction of the x. So, remove the minus and interchange the limits. We know the limits from 60 to 45. Interchange the limits, we get the length of the pipe. Length is 22.6 meters. Okay, the next question will be, in a cylindrical fuel rod of nuclear reactor, heat is generated internally according to the equation. Such questions are slightly maybe complicated, because it is a non-uniform heat generation. There is a cylindrical fuel rod, nuclear fuel rod. Here the heat generation is happening, but non-uniform heat generation. Why it is non-uniform? Because you see that heat generation rate is a function of the R, where R naught is the radius of the rod. Okay. Radius is always measured from the axis. So, at different locations, at different values of R, there is a different amount of the heat is generated. So, it is a non-uniform heat generation. This is, I can write that, this is the non-uniform heat generation. Earlier, one problem I have done, for the sphere there is a heat generation, but there it is uniform heat generation. Here it is a non-uniform heat generation. Okay. See that where Qg is the local means at a particular location. At a particular location, what is the heat generation rate has been given. R naught is the radius of the that cylindrical rod, and and Q naught is the heat generation rate at the axis. With reference to the axis heat generation rate, here what is the heat generation rate has been given. The rate of heat removal per unit area from the surface, assume steady state. Yes, assuming steady state. I already said, assuming steady state, whenever there is a heat generation, for steady state, all the heat generated must be convected from the surface of the wire, from the surface of the body by convection. Okay, right. First, I would like to calculate what is this is the heat generated, which is a function of R. What is the total heat generated in the entire volume? If L is the length of the rod, what is the heat generated for a differential control volume? I will consider total heat generated will be, it is per unit volume. See that, heat generated per unit volume, that is Qg into volume of rod. Qg into volume of that. What is that Qg? Q naught into 1 minus integral 0 to R naught Qg into 2 pi R L dr. Okay. Supposing if you see the cross section of that rod, for a differential, for the differential control volume, I consider that this is R, this is dr. If the L is the length of the rod, so what is the differential volume of this particular hatched one? 2 pi R into dr, that is the area, into length, 2 pi R into L. Qg is the at that location, what is that heat generated at that location, this has been given by that. Okay. That will be taken as integral 0 to R naught Q naught into 1 minus R square by R naught square into 2 pi R L dr. L is the length of the rod. Length of the rod has been, if the length is not given, you can take per unit length. Or you can, because heat transfer rate per unit area has been asked, we can calculate per length for a length L of the rod. Please note that what I am doing that. Try to understand. If R is the radial direction coordinate, I consider a differentially small control volume of increment in radius is dr, differentially small control volume. At that location, heat generation is Qg, right? So what is the volume of that hatched one? 2 pi r into dr, that gives the area into length. Okay, that is a differential control volume of the elemental volume I have considered. That into Qg has been given. That will give us the heat generated only within that. So that will be, because what is the volume of the differential control volume? Differential volume there 2 pi r into dr, 2 pi r into dr into length. That multiplied by Qg will be give the heat generated only within the differential control volume. That will be integrated from R is equal to 0 to the R is equal to R naught. Okay. Then we will get the total heat generated. This is the total heat generated. What after integration, what you get is the, after integration, what you get is the, like this, total heat generated in entire rod pi r L dr. Okay, after integration you will get 2 pi L Q naught into R naught square by 4. This is the total heat generated, okay, in watts. The rate of for steady state, Qg should be equal to the total heat convected from the surface. That is, should be equal to the heat flux. Because look at this, what question has been asked there? The rate of heat removal per unit area, which is also called as the heat flux. Okay, heat flux into heat flux, that is heat transfer rate per unit area. What is the meaning of that heat flux? Heat transfer rate per unit area into total heat convected, total into what is the area there? Pi r square, that is pi r naught square into length. That is the, sorry, this is not the, this is the volume. Heat flux into area of convection. That should be equal to the heat flux into, what is the area of convection? What is the area of convection? 2 pi r naught into length. For a cylindrical body like this, what is the total area of convection? 2 pi r naught, that is the perimeter, into length. Okay. So first what I have calculated is, if this is a cylindrical rod, I took a small differential control volume of differential elemental increment in length. I took a small differential control volume. For that, what is the heat generated? I have calculated. That has been integrated. What is the, for that particular differential control volume, what is the heat generated? What is the volume of that into Qg? Because this Qg is the rate of heat generation per unit volume. So per unit volume, this is that I have to multiply with that because Qg into what is the volume of this? 2 pi r dr into length. Okay. Then that has been integrated from 0 to r naught to get the total heat generated. For steady state, whatever the heat generated in the entire rod should be equal to the heat transfer rate from the entire rod to the fluid. What is the total heat transfer rate? Heat flux into area of heat transfer. What is the area of convection heat transfer? 2 pi r naught into length. See this, 2 pi r naught into, from this we can calculate heat flux. Heat flux means what? Heat transfer rate per unit area. We got this as Q naught R naught by 4. Okay, Q naught R naught, because this has been already obtained. What is the Qg we have obtained? 2 pi L into Q naught into R naught square by 4. That and this should be equated. See, from that you will get the heat flux. First I calculated the total heat generated. That should be equal to the heat transfer rate from the entire surface of the rod. How to calculate the heat transfer rate from the entire surface of the rod? Heat flux into total convection area. What do you mean by flux? Heat transfer rate per unit area is called as a flux. That flux word, you use it only in this subject. Whenever you use the word heat flux, it means heat transfer rate per unit area. He has asked to calculate the heat flux. Heat flux into total convection area, that is 2 pi r naught into L. That should be equal to the total heat generated in the entire rod. So this is also a very good question, because it is the case of non-uniform heat generation rate. Look at this. This is a sixth question. By seeing that, you can easily tell it is a fin problem. It is a problem of the fin, because a rod is connecting between two walls which are maintained at a temperature of 120. A 90 mm by 90 mm iron bar of 0.6 meters long is connected to the wall of two heated reservoirs, each at 120. The ambient convection heat transfer coefficient. The ambient convection heat transfer coefficient is the temperature of the bar midway between the, here is asking, at this exactly at the midsection is asking. Okay, the temperature of the fluid will be, air will be 25 degrees Celsius, convection given. So from the symmetry, I could easily say that this is the temperature profile. The minimum temperature will be seen at the, what is the temperature at the midway between. So we need to calculate what is this temperature. So if we just cut this portion and remove this, we just think of that, this is an insulated. You can be considered as the insulated case. Now if you just cut this portion and if you take it, I could take this as like this. Instead of 2L, I can take it as the length here. The temperature drop will be like this. This can be taken as an insulated tip. For the insulated tip case, now the length of the rod is only L. This is the base temperature T naught 120. For this insulated tip case, see this is the, from the symmetry, this is the temperature profile along the length of the rod. This side 120, this side 120. From the symmetry, we can get the temperature profile like this, where at the mid plane of the rod, temperature is minimum. Okay, what is the temperature we need to calculate? For that, if you just cut off here and remove, the temperature at the mid plane will be the minimum. That mid plane can be considered as an insulated tip case. Once again write, this is the fin, this is the length of the rod is L. Now it is not 2L because I already removed that symmetry. This is an insulated tip case. What is the temperature at X is equal to L? This is the base temperature. Okay. Now for this insulated tip case, what is the temperature distribution is given by, for the insulated tip case of fin, T minus T infinity by T naught minus T infinity is equal to cos H, hyperbolic cos H m L minus X divided by cos H ml. This is the temperature distribution for the insulated tip case of a fin. Generally fin problems, there usually you get three cases. One is infinitely long fin. Second thing is the insulated tip case, insulated fin. This is, see, this hatching says that this is an insulated tip. How do you know that it is an insulated tip? Because at this location, see this, at this location dt by dx will be 0 because temperature is minimum there. Temperature is minimum there. Here the dt by dx at this location is 0. dt by dx is 0. Based on that, I can say that it is the insulated tip case. Now, because he has asked that x is equal to L here, now if you put x is equal to L, it becomes 1 because it becomes 0, 1 by cos HML. What is that M formula? M is given by root of, M is given by root of HP by Ka. What kind of fin it is? It is a square fin. It is a, look at this, 90 by, perimeter will be, perimeter. Now it is a square fin like this. This is 90, this is 90, this is the perimeter, this is the perimeter, okay. Perimeter will be 4 into 90 divided by 1000 meters. This is the P is the perimeter, perimeter of the fin. Mostly fin will be of circular cross section, mostly 99% cases it is a circular cross section which is called as a pin fin. But sometimes it may be rectangular fins. Fin may have a different, this is a square fin, okay, there are hyperbolic fins, okay, there are varieties of fins will be there, but most commonly two things are common. One is a rectangular fin, second thing is a pin fin, but it is a square fin, A, this is a A there, this is the area of cross section. A will be 90 by 100, sorry, 90 by 1000, 90 mm there, into 90 by 1000, this is the A will be there, okay. 90 mm, this is 9. So, the area of cross section, profile area, area of cross section or profile area. I request you to chart with me and ask the doubts. If you have any, I would be able to clear your doubts. Now, first you calculate any fin problem, first we have to calculate this M value, where P is the perimeter, A is the area of cross section, H is the convection heat transfer coefficient. M value, I got here M value as 4.13 per meter. So, for insulated tip fin, already given T minus T infinity by T naught minus T infinity is equal to cos H M L minus X by cos HML. Put X is equal to L. Then it will become T at X is equal to L, which we require. What is that ambient temperature? 25. Base temperature is 120. 25. 1 divided by cos hyperbolic cosine. M value has been calculated as 4.13. And length will become 0.3 because 0.6 is the total length. So, 2L is the total length, 0.6. Now, it becomes 0.3. You will get the answer as temperature at X is equal to L, that mid plane, which will be 75.72 degrees Celsius. So, I will explain once again the concept. It is a fin is connecting two reservoirs which are at the same temperature. Therefore, the temperature profile will be symmetric about the mid plane. We need to calculate the temperature at the mid plane. Now, if we just cut it off and remove that, this mid plane can be considered as this is the new configuration it will become. The mid plane will become the insulated tip case, because there the dt by dx is equal to 0 because the temperature is minimum. When dt by dx is 0, there is no conduction at the, suppose if you just remove this, there cannot be any conduction there because conduction formula is minus Ka dt by dx. When dt by dx is 0, there is no conduction there at that tip. If you just cut it off and remove, no conduction here. Q conducted here is equal to 0. That is why it is called as the insulated tip case. For that insulated tip case, this is a temperature distribution within the fin. And because he has asked at this location, because what is that x here? Here x is the direction, no? This is the x direction. This is the x direction. This is the x direction. X is equal to 0 at the root of the fin. This is called as the root temperature. This is called as the tip temperature. Any fin has got, x has got two limits. One at the root, that is where the temperature is T0. Other at the tip of the fin, where at the end of the fin or the tip of the fin, where the x value is L. L is the length of the fin. I just cut it here and remove that portion. Now this will be look like this, and this is an insulated tip case problem. Almost all the fin problems by default, any fin problem you get in the gate, by default you consider it as an insulated tip case, you will get the answer. Unless very clearly mentioned that it is a very long fin, infinitely long fin, but that is a rare case. Most of the fin problems will be solved by the insulated tip case formula. Here the formula for the heat transfer rate also I would like to give you here. The formula for the heat transfer rate will be, this is also fin, square root of Hp Ka into T0 minus T infinity into tan HML. This is an hyperbolic tan. Just like it is a hyperbolic cosine, it is a hyperbolic tan, where L is the length of the fin. M is given by root of Hp by Ka. Its units are 4.13 per meter. P is the perimeter and A is the profile area or the cross-sectional area of the fin. If this is a fin, this is a perimeter, and this area is the cross-sectional area or profile area. In this case, it is a square fin, therefore profile area will be 90 by 90. Right. Now, a double pipe heat exchanger of 20 meter length, a hot fluid flows in the annulus in the inner pipe. Okay. This is the pipe in pipe or double pipe. Concentric tube is also they call pipe in pipe or double pipe. A cold fluid flows in the inner pipe. This is a cold fluid. So, a hot fluid flows here, cold fluid, and here it is a hot fluid. He has not mentioned which is what kind of heat exchanger it is, because heat exchangers could be of three types: parallel flow, counter flow and cross flow. First let me check what kind of heat exchanger is. First here for the hot fluid, I will calculate here from this, put x is equal to 0, at x is equal to 0 implies temperature will be 100, that is Thi, and The exit will be, what is the length of the pipe? 20. 100 minus 1.5 into 20. 1.5 into 20 will be, this will be 30. 100 minus 30, it will be 70 for the cold fluid. Okay, fine. Now, for the cold fluid, at x is equal to 0 for the cold fluid, put x is equal to 0 here, Tci will be 18, Tce will be 18 plus 3.5 into x. X is 20, 3.5 into x. Yes, okay. 3.5 into x, it becomes 88 degrees Celsius. So I can confirm here that we are saying that Tce is greater than The. This is possible only in counterflow. Possible only in counterflow heat. Cold fluid exit temperature can be more than hot fluid exit temperature only in the counterflow heat exchanger, where the profile may look like this. This is a hot fluid, this is the cold fluid, this is a counterflow heat exchanger. This is not possible in parallel flow. In parallel flow heat exchanger, this is never possible. Cold fluid exit cannot be more than the hot exit. So this what he has calculated is LMTD has asked. For the, we know that Thi, The, Tci, Tce. So this is delta Ti, this is delta T. We know the LMTD formula. LMTD of the counterflow will be delta Ti minus delta Te divided by Ln delta Ti by delta Te. We know all the four temperatures. You got it here. Thi is 100, Th is 70, Tci is 18, Tce is 88. You substitute here, you will calculate this difference, Thi minus Tce. This difference is the delta Ti. THE minus TCI, this difference is the delta T. You can easily calculate. THI is 100, 100 minus 88, it will be 12 degrees. Delta TE will be, THE is 70, 70 minus 18, 70 minus 20 is 50, 52. You substitute there, you will get the LMTD. LMTD, you will get it here as 27.28. This is definitely a counterflow heat exchanger. How did they decide that? TCE is greater than THE. By putting x is equal to 0 and here x is equal to 0, here x is equal to L, length of the heat exchanger. This is a cold gas goes like this, or if the hot is going like this, cold is coming like this. It is a counterflow. Both the fluids are commuting in the opposite direction. I got the THI, I got the THE, I got the TCI, I got the TCE, and I substitute, I got the delta Ti and delta TE, and I obtained the LMTD. Right? An insulated cylindrical pipe has a surface temperature of, it is exposed to black body surroundings. Emissivity of the surface is given is a radiation problem. Convection heat transfer coefficient outside the insulation surface is 5.30. Surrounding fluid may be assumed as a transparent. The percentage contribution from the radiation to the total heat transfer rate. There is a pipe. The pipe, cylindrical rod, cylindrical. The pipe is losing heat by convection and also by radiation. There are two different modes of heat transfer occurring simultaneously. Convection is happening. Convection heat transfer rate is given by HA delta T. First I calculate from the Newton's law of cooling what is the convection heat transfer rate. HA delta T. H value is given as 5.30. Area, delta T, area per some area you can take because he has asked only percentage. What is the temperature of the rod? The surface temperature of the rod is 60 degrees Celsius. 60 minus, what is the temperature of the fluid? Air, no? Temperature of the air is been given as 27. Delta T, HA delta T means temperature difference between the solid body and the fluid, 60 minus 27 watts. This is the rate of heat transfer by convection only. Then the rate of heat transfer by radiation. A body kept in a large enclosure in the surroundings, that this is a formula. Please remember, epsilon sigma epsilon into temperature of the rod to the power of 4 minus temperature of the surrounding into area. This is the formula for the radiation heat loss. Whenever there is a body kept in a, whenever there is a finite sized body kept in a large enclosure or the large surroundings, surrounding temperature is T infinity, this is the temperature of the rod and everything is given. But only thing here, the TW we have to keep only in Kelvin. All these temperatures of the radiation T infinity is 27 plus 273 Kelvin. For radiation, please you have to convert the temperatures only in Kelvin scale. Emissivity has been given. Emissivity is 0.92, that has been given. Sigma is the Stephen Boltzmann constant, 5.67 into 10 power minus 8. Okay. Therefore, percentage heat loss by radiation out of the total heat transfer rate, what is the percentage heat loss by radiation alone? That is Q by radiation, heat loss by radiation divided by Q convection plus Q radiation. That will give the percentage heat loss by radiation only. Please note that whenever there is a finite sized body is kept in a large enclosure, this is the formula for calculating the radiation heat transfer rate. Sigma epsilon temperature of the body to the power of 4 minus temperature of the ambient to the power of 4 into area, surface area of the body. But A gets cancelled here, we don't have to consider that area because in the numerator and area is there here also. You will get the answer as 55.59%. This is the percentage heat loss by radiation out of the total, because there is a simultaneous heat loss by convection and as well as the radiation simultaneously. Right, next question will be a grey diffuse opaque surface. What do you mean by opaque surface? A opaque surface, there is no transmissivity. For opaque surface, tau is equal to 0. Transmissivity is 0. Therefore, alpha plus rho is equal to 1. Absorptivity plus reflectivity is equal to 1. Rho is the reflectivity and alpha is the absorptivity. Radiosity, what does it mean by definitely radiosity? Radiosity means if there is a body, radiosity means the total radiation leaving a surface is radiosity. Irradiation means the total amount of the incident. This is the incident. This is the leaving. This is called radiosity. J is the radiosity, incident is the irradiation. J is equal to, I can write like this because total energy will be leaving will be, what is rho G, reflected energy plus emitted energy, okay, epsilon into EB. Epsilon is alpha, alpha is 1 minus rho, okay, rho is equal to 1 minus alpha, 1 minus alpha into G, G is the incident radiation, this is the emitted part, this is an emitted part, epsilon into EB, but alpha is equal to epsilon from, this is the Kirchhoff's law. A good absorber is always a good emitter. Absorptivity is equal to emissivity. But according to the Kirchhoff's law, absorptivity is emissivity, that can be written as 1 minus epsilon into G plus epsilon into sigma into T to the power of 4. Everything is given. Alpha is given. You can substitute here. Alpha is 0.75. Irradiation is, this is irradiation. G is called irradiation. Incident radiation. This is called radiosity. J is the radiosity. Therefore, J now this here in this problem epsilon is alpha, according to alpha has been given here 0.75 into sigma Stephen Boltzmann constant 5.67 into 10 power minus 8 into 240 plus 273 to the power of 4. You will get the answer as 3345.19 watt per meter square. A parallel flow heat exchanger has hot and cold water streams. He has given in any heat exchanger, remember, if the three temperatures are given, remember in any heat exchanger problem here, Remember that there are two methods there. Any problem of heat exchanger in heat transfer subject can be solved only by two methods. One is LMTD method and other is the effectiveness NTU method. The main purpose of the LMTD method is to design the heat exchanger or to calculate the area of the heat exchanger. Look at this, the area is asked. That means you have to go to the LMTD method. Whenever you want to calculate any one exit temperature or two exit temperatures, go to the effectiveness NTU method. Just by reading the problem, we can guess which method is to be used. If you are given the 3 temperatures or 4 temperatures, yes, go to the LMTD method. If you are given only the 2 temperatures in any heat exchanger problems, you can solve it only by the effectiveness NTU method. So here the problem has the 3 temperatures are there, TH1, TH2, TC1. That means you can use LMTD method only. So first he has given the has given 4 temperatures or 3 temperatures, only 3 is given. How to get the 4th temperature? From energy balance. From energy balance equation, m dot h Cph Thi minus The is equal to m dot c Cpc Tce minus Tci. He has given Thi, The given, Tci given, you can calculate the Tce there. Then decide which type of heat exchanger, parallel flow. Immediately we can draw the temperature profiles and you know all the 4 temperatures, Thi, The, Tci, Tce. Now this can be obtained as delta Ti. This is delta Te. Because we are going to follow the LMTD method, we have to calculate the LMTD. What is the Thi there? 70. This is 70. The will be, this is 40. Tci will be 20. Tce has been obtained there. We know the Tce also. Now calculate this delta Ti, delta Te, then you can calculate the LMTD. Delta Ti minus delta Te divided by ln delta Ti by delta Te. You get the log mean temperature difference of the parallel flow heat exchanger. Then you can use the Q is equal to UA delta Tm. Is the U given there? No. It is, U is not given. It can be calculated. If U is not given, it could be obtained from this formula, 1 by Hi plus 1 by Ho. From that, U has been obtained as 32.5. With the overall heat transfer coefficient, what is that U there? Overall heat transfer coefficient. Mostly in the gate problems, U will be given. Here it is not given. The convection heat transfer coefficients inside the pipe and outside the pipe has been given. If the U is not given, overall heat transfer coefficient is not given, you can obtain like that. Once you obtain the U there, you can use this formula. U is equal to UA delta Tm. What is delta Tm? LMTD. LMTD means delta Tm, log mean temperature difference, which should be equal to the m dot h Cph Thi minus The. Therefore, area can be obtained. Then the area is m dot h Cph, because this is the rate of heat transfer divided by U into delta Tm. We get the area as 28.06 meter square. The only precaution here is always keep this in joule per kg Kelvin. Never keep it in kilojoules, because the U is always in watt per meter square Kelvin. For the compatibility of units, for satisfying the units, always keep that specific heat Cp, particularly while calculating the area or while calculating the rate of heat transfer. What is this? What is this one in the heat exchanger problem? It is the total rate of heat transfer between hot and cold fluids. Total rate of heat transfer between hot and cold fluids. This Q. Okay. So all the problems of heat transfer I have discussed it there. Now I am going to discuss the thermodynamics. Just take a 5 minutes break. After the break, I will give the discussion regarding the heat thermodynamics subject also. Just take a break for 5 minutes. Hello students, welcome back to the class. This video class is pertaining to the discussion on the thermodynamics questions which I have written a few days ago. Thermodynamics also, like heat transfer, is very important subject in GATE point of view. The average weightage will be around 6 to 7 or 7 to 8 marks. Thermodynamics will be, and most of the questions in thermodynamics, they will be pertaining to the steady flow energy equation, entropy, second law of thermodynamics, thermal efficiency, COP, Carnot cycle, Carnot heat engine, reversal Carnot cycle, Clausius inequality. These are the main areas we have to focus. Whenever you are preparing for the thermodynamics GATE syllabus, there are certain areas where you have to keep extra attention, extra focus. That is this steady flow energy equation, because that is the first law of thermodynamics applied to any steady flow open system like turbine, compressor, nozzle, diffuser, etc. Okay. For such devices, the steady flow energy equation is the basic: turbine, compressor, nozzle, pump, etc. For all these things, that is one important, very important equation. That is the first law format: steady flow energy equation, known as SFEE. And also sometimes they may ask the question regarding the closed system: Q minus W is equal to delta U, first law. Or otherwise you may focus on the entropy questions, or otherwise you may mostly the GATE questions will be pertaining to the Clausius inequality, cyclic integral of this SF. Certain areas we have to give more, that is this equation Q, first law, first law equation, or otherwise cyclic integral of delta Q by T is less than or equal to 0, less than sign for irreversible cycle, equality sign for the reversible cycle, and the entropy changes delta S during various thermodynamic processes, and properties of the pure substances, pure substance properties, and thermodynamic relations. So these are the certain areas where you have to give the more focus. Right. Now let me solve all the questions which are written in the examination pertaining to the thermodynamics. The work done by 1 mole of gas obeying van der Waals equation of state. What is first of all this van der Waals equation of state? You are all aware that ideal gas equation is PV is equal to MRT, or PV is equal to nRT. This is a universal gas constant, or sometimes small v is RT. Anyway, all these are formats of the ideal gas equation, which is also called as the perfect gas, which obeys all the gas laws at all pressures and temperatures for the ideal gas. So according to the kinetic theory of gas, the ideal gas behavior will be entirely different. It has got certain assumptions. According to the assumptions of kinetic theory, the ideal gas molecules have no volume, but they have the mass. The molecules of the ideal gas or the perfect gas, they have the mass, but there is no volume. That is why they are called as the point masses. Number one. Number two, there are no intermolecular forces of attraction or repulsion among them. There are no intermolecular attractive or repulsive forces among the molecules. That is another assumption for the ideal gas behavior. The third assumption, all the collisions among the molecules are supposed to be perfectly elastic. Okay, that is the coefficient of restitution is 1. Okay, perfectly elastic. All the collisions among the molecules are perfectly elastic. These are certain assumptions regarding the ideal gas behavior, right, according to the kinetic theory. Based on this equation has been put up. Now, is all the gases are ideal? No. There are certain practical gases which are also called as a real gas. A real gas is supposed to obey the van der Waals equation of state, that is P plus A by V square into V minus B is equal to RT. In fact, in this B will, in the real gas behavior, the molecules possess volume. If the molecules of the ideal gas have 0 volume, but they have the mass, the molecules of the real gas will possess certain volume. Supposing if you pack all the real gas molecules in one corner, if you just pack them up, if you just pack all the molecules, that volume occupied by all the, if V is the volume of the gas and B is the co-volume. If you pack all the molecules to the corner of the container, then that volume is called as the co-volume, because all the molecules are possessing, if they are all clustered or packed into one corner, that volume occupied by the real gas molecules, total volume occupied by the real gas, it is called as the B. And where A is the term pertaining to the intermolecular cohesive forces. So finally, this is the van der Waals equation of state meant for real gas. If A is equal to 0, B is equal to 0, then that will become the ideal gas. Okay, understood? Ideal gas behavior is different. Ideal gas is something like a imaginary, theoretical. There is no practical ideal gas, but we consider that air, oxygen, nitrogen and all these diatomic, monatomic gases are treated as ideal gases for doing the problems. But steam, is the steam real gas or ideal gas? Means steam is definitely a real gas. A refrigerant is a real gas. So ideal gas behavior is something as imaginary or theoretically obeying this PV is equal to MRT or PV is equal to nRT. N is the number of moles. This is the ideal gas, universal gas constant. Now for this, if the van der Waals equation of state, if it is undergoing a reversible isothermal expansion from its initial volume Vi to the final volume Vf, then what will be the work done? He is asking the work done, he is asking. So process is reversible. Therefore, for any reversible process, it is integral PdV. From this equation, what is that P? P is equal to RT divided by V minus B minus A by V square, right? I substitute that. Integral, what is the P? RT divided by V minus B into A by V square according to the van der Waals equation dV between the limits V initial Vi to the V final. Because for any closed system undergoing a reversible process, the work done formula, general work done formula will be integral PdV. Integral PdV is the formula written for work done by a closed system during a reversible or quasi-static process. Please remember, integral PdV is the formula written for a closed system undergoing a quasi-static or reversible process. If it is a minus integral VdP, not PdV, integral VdP, this is a steady flow work done during a reversible process. For an open system, steady flow work done by closed system is integral PdV. Steady flow work done by a open system, see that integral PdV is written for a closed system and reversible process. Minus integral VdP is written for the work done by a steady flow open system during a reversible process. Both are for the reversible process only. Only for one particular thermodynamic process, integral PdV and integral VdP both will become equal, that is isothermal process. Only for the isothermal process, integral PdV and integral VdP both will be equal. Integral PdV for the closed system, minus integral VdP for the steady flow open system, that too for a reversible process. Try to understand the gap. Now we have to integrate this equation. This equation will become now integral V initial to the V final RT by V minus B, it become RT by V minus B minus A by V square dV. It will become RT, taken common, that is log V minus B plus A by V between the limits Vi to the Vf. It will become RT log Vf minus B divided by Vi minus B plus A into 1 by Vf minus 1 by Va. This is the answer for the work done. Please note that integral PDV can be written only when the system is closed and the process is reversible or quasi-static. So this is answer. A system undergoes a cyclic process consisting of 3 as mentioned in the table 1 to 2, 2 to 3, 3 to 1. Compute ABCD is asking from this table. So assuming that system is closed, assume closed system, Q minus W, first law of thermodynamics, delta U or delta E I could write. Sometimes some books write the E, some books write the U. E or U both mean the same, internal energy. Q is the heat transfer. So it has got some sign convention. Remember that it is got sign convention. Q is positive if supplied to the system. Q is positive if supplied to the system. Q is negative if rejection. W is positive if done by system, work done by the system, that is an expansion work. W is negative if work done on system, that is a compression work. Any compression work is a negative, any expansion work is a positive. Whenever heat is supplied, that is treated as a positive. Whenever heat is rejected from the system, it should be treated as a negative. Remember that. Okay, supposing if you take a tubelet as a system, there the heat transfer is from the system to the surroundings. Because bulb is hot, that should be considered as a heat rejection, negative heat transfer is negative. Fine. Now consider for the process 1 to 2, if you take you require that Q minus W is how much, 100, is equal to change in internal energy is 150, that is A is Q there, implies A is equal to 150 plus 100, that will become 250. A, you got it. For any cycle, for any thermodynamic cycle, because thermodynamic property is internal energy, cyclic integral of dE is equal to 0. Because most of the books internal energy is written by U, but here it is given the written as E, no problem. We have to add up all these delta E's. 150 plus C minus 250 should be equal to 0. For any thermodynamic cycle, please remember, because internal energy being a property, internal energy is a property. Heat and work are not properties. Heat and work, they are not properties, they are path functions, they are inexact differentials. But all other things like pressure, volume, internal energy, enthalpy, entropy, they are all the properties. The cyclic integral of differential of any property is 0. From this, C can be obtained as 250 minus 150, it will become 100. C is 100. We got A and C. For the, if you just like this, for 2 to 3, for 2 to 3 process, if you write Q minus W, no, Q minus, what is that Q? This formula I am writing. This is the formula I am writing. What is the Q there? 100 minus W will be 250 minus of minus 250. Here minus sign is given. No, sorry. Q minus W. W here is B. No, not B, D. 100 minus 100 minus 100 minus D is equal to delta I. Delta I is given as minus 250. This will become, D will go to the right side, 250 will come to the left side. 250 will come to the left side, becomes 250 plus 100, 350. Right? D will be 350. I got all the answers, 250, 100, 350. Answer will be 250. C, A is 250. B will be C, we got it. For the 2 to 3, sorry, I have written a wrong way, I think. 1 to 2 is A, we got it. For any thermodynamic cycle, this from this we got the C. Now, if you write for the process 2 to 3, I write here for 2 to 3, if you write here Q minus W, Q is B minus W minus of minus 60 is equal to delta E, that is C. C is 100, we got it, right? That means B plus 60, 100 minus 60, B will be 40. Okay, right. Now you got the answers 250, 40, C is 100, D is, the answer is B. B is the answer. B is the answer. I got same equation, Q minus W are written, but for getting the C, I have written the cyclic integral of dE is equal to 0, because internal energy is a property. For your information, I would like to tell that cyclic integral of differential of any thermodynamic property, it is 0. For any cycle, this is valid. Please remember that. So property is a point function. For any point function, cyclic integral of differential of any property, when I say property, it may be pressure, it may be volume, it may be temperature, it may be internal energy, U, or it may be enthalpy, or it may be entropy, for anything. Okay. To determine the thermodynamic state of gaseous argon in contact with liquid water. Argon is in contact with water. Argon, this mixture, it is a pure substance. This mixture can be called as a pure substance containing two different components. Argon plus water. The number of independent thermodynamic properties. The minimum number of intensive properties or thermodynamic variables required are C minus P plus 2. Okay. This is called Gibbs phase rule. This rule is called as Gibbs phase rule. What is meant by Gibbs phase rule? It is the minimum number of intensive properties required or number of independent variables. Number of independent variables to describe the state of a system. C is the number of chemical components. So here 2 are there. How many phases are there? 2. So F will be 2. This is called Gibbs phase rule. Minimum number of independent thermodynamic variables according to the Gibbs phase rule will be C means number of chemical constituents. 2 are there, argon and water. How many phases are there? Gaseous water. Gas, this is a gas. This is a liquid. There are 2 phases. P value will be 2. Number 2 phases, 2 chemical constituents. Therefore, the minimum number of independent thermodynamic variables will be 2. During an adiabatic process, the cube of the pressure P cube is inversely proportional to the V to the power of 5. Okay, this is the P cube into V to the power of 5 is equal to constant. P into V to the power of 5 by 3 is equal to constant. For adiabatic process, equation is PV to the power of gamma. For the reversible adiabatic process, PV to the power of gamma is constant. Therefore, here gamma will be 5 by 3. Gamma is known as, what is the name of that gamma? Adiabatic index, Cp by Cv. The new linear temperature scale is denoted by P has been developed, while the freezing point of water is 150 P and boiling point is 400 P, then 500 P in degrees Celsius will be. We all know that C by 100 is equal to F minus 32 by 180, the conversion, where F is the Fahrenheit. No? This is a Celsius. Similar thing we have to, okay, here P, this is the ice point, this is the freezing point, this is the boiling point, scale difference. P minus, what is that freezing point? Freezing point of water is 150 divided by, what is the difference? Boiling point is 400, freezing point is 150. Okay, that is 400 minus 150. Put P is equal to 500. Implies Celsius we get. C will be how much? C will be 140. This is a Fahrenheit scale. This is a Celsius scale. Similarly, we have got another scale. This is the difference between boiling point and freezing point. Boiling point is 400, freezing point is 150. Put P is equal to 500, corresponding Celsius will be 140. A saturated liquid at 1400 kilopascal with enthalpy of 700 is throttled to a liquid vapor mixture. At the exit conditions, enthalpy of saturated liquid is the percentage of original liquid to which vaporizes is. He is asking the dryness fraction. Throttling is isoenthalpic process, constant enthalpic process. Throttling is constant enthalpy process. That is why on the enthalpy versus entropy diagram, if you just look at the it goes like the horizontal. The process goes like a horizontal. This is the liquid one. This is a constant enthalpy process. Entropy increases. During throttling, entropy increases, pressure drops. Delta P will be less than 0, delta H is equal to 0, delta S is greater than 0. This is the graph on the H versus S. Okay. He is asking you to calculate what is the dryness fraction here, because H1 is equal to H2. What is H1? HF is equal to HF plus X into HFG. At what pressure? At P2 of 150, no? 150, initially is a 150 kilopascal. There it is 1400 kilopascal. So liquid enthalpy is with an enthalpy of 700 is equal to, here the HF is 500 plus X into HFG is Hg minus, this is Hg. This is Hg minus HF. 2500 minus 500. You will get the X. The dryness fraction, we got it as the 0.1, 10%. Please note that enthalpy is constant enthalpy process. During enthalpy, the pressure has to drop. Enthalpy is an irreversible process. That is why entropy increases. Enthalpy is an irreversible adiabatic process. That is why entropy of the fluid will increase. Look at this. The process goes rightwards. Entropy clearly is increasing. We have calculated the dryness fraction. A saturated liquid is after throttling, some of the liquid is vaporizing. Therefore, that final dryness fraction, we got it as the 10%. HF is equal to HF, because we know that it is a wet vapor. Initially it is a saturated liquid. Therefore, that is why I have written this as the HF. This HF is a saturated liquid, clearly as mentioned here, saturated liquid. So, a saturated liquid is undergoing a throttling. After the throttling, there is some vapor appearing. X is greater than 0, that is, we have calculated the dryness fraction of that wet vapor after throttling. Water is heated in atmospheric pressure from 20 to 90 using two different processes. In process 1, heating is done by a source of 90. In process 2, heating is done from 20 to 50 by a source of 50, and then from 50 to 90 by another source at 90 degrees Celsius. Which of the following is correct? See, in the first process and second process, the enthalpy change is same. the delta H enthalpy change is mCp delta T. This change of temperature is same in the initially from 20 to 90 directly we are heating. In second process from 20 to 50 first and 50 to 90 next. But from 20 to 90 the change of temperature is same. So delta H is same in both the processes. But entropy changes are different. See, entropy is something connected with the irreversible. If the heating is carried out in steps, say from 20 to the 90 in one case, in another case is 20 to 50 and 50 to 90 from two different sources. In the second case, the heating is carried out in steps. Therefore, irreversibility is lesser, entropy changes are lesser. Process 2 is more reversible than or lesser irreversible. Actually, this word is not correct actually, to be precisely speaking. Process 2 is lesser irreversible than process 1. If you write like that, it is correct. Process 2 is less irreversible. The irreversibility carried during the second process is lesser as compared to the first one. Why the irreversibility is lesser? Because you are doing the heating in steps. Supposing if the same heating is done in 3 steps, say from 20 to the 40, 40 to the 60, 60 to the 90 from 3 different sources, then definitely the irreversibility will be more the irreversibility will be even further lesser. If the heating is carried out in more and more number of steps from different sources, definitely the irreversibility associated will be lesser. There will be a lesser entropy generated in the universe. Supposing if you take infinite number of stages of heating, say from 20 to the 20.1, 20.1 to the 20.2, like a bite from different sources, heat sources, definitely the process may approach finally the reversible process. So the answer will be process 2 is more reversible process than process 1. So try to understand. If your heating is carried out directly from 20 to the 90 from certain source at 90, see that using heating is done by source of 90, then more irreversibility, more entropy generated in the universe. Instead of that one from 20 to 50 from source at 50 and again 50 to the 90 from the source at source means which is supplying heat, then the entropy generated will be lesser. The process is carrying lesser irreversibility. Entropy generated in the universe will be lesser. If the heating is done in 4 steps instead of 2 steps, the irreversibility will be further reduced. Irreversibility will be further lesser. So answer is C. But enthalpy changes in all the processes is same because the final temperature change from 20 to 90 it is same in both the processes. Heat capacity is given. The heat capacity and increases there, then the change in internal energy. Q minus W is equal to delta U. For calculating Q, integral delta Q, we have to do it. This is the T1. What is the process there? Constant pressure process. Integral Cp dt. Maintained at a pressure of 1 meter. That is integral T1 to T2. I substitute that 3 plus 40 by T plus 100 dt. What is the temperature limits there? From 0 to 100. Or temperatures is in I think is in Kelvin there. Temperature in Kelvin, therefore I have to keep the limits as 273 to the 100 means it is 373 because he has kept the Kelvin scale here. Temperature is in Kelvin. Therefore, we have to calculate that Q will be 309.5 joules. Work done will be, because it is a constant process, constant pressure process, P into V2 minus V1, it is a constant pressure process, that is pressure is given 1.013 2 into 10 power 5, 2400 minus 2000 centimeter cube, no? That is why I convert it into the meter cube. This is 40.5 joules. Now I write the first law of thermodynamics. Q minus W is equal to delta U, that is 309.5 minus 40.53, 268.9 joules. I just got the, because it is a constant pressure heating, Q is given by mCp delta D, M is taken as 1 kg, because heat capacities were given for all the, look at this. So, Cp into delta T, Cp is given as a function of temperature, but temperatures must be kept in Kelvin. That specific heat Cp is substituted between the limits 273 and 373. It is a constant pressure heating. Therefore, it is Cp into dt. Work done is, because it is a constant pressure work done, P is taken out, P into V2 minus V1, and volumes are given in centimeter cube. I have converted into the meter cube, right? And then I have used the first law of thermodynamics, Q minus W is equal to delta U. I got the change of internal energy. A large furnace can transfer heat at a temperature of 1100 Kelvin at a steady rate of 4000 kilowatts. The rate of exergy flow. Exergy is a very important concept, which is also called as available energy, which is also called as available energy or exergy. Unavailable energy is called as energy. What is the available energy? Available energy is the maximum useful work you can obtain by when the system is, that is the maximum work obtained only when the process is undergoing a reversible. Okay, only when a reversible heat engine like a Carnot heat engine can provide you. Reversible heat engine can provide you the maximum useful work. That maximum useful work that could be obtained is called as an exergy, also known as an available energy. A source is there at a temperature of a large furnace at a temperature of 1100 Kelvin. 1100 Kelvin. And it is able to supply 4000 kilowatts. The maximum work you may obtain only when in a reversible heat engine with a sink temperature of the environment 25 plus 273 Kelvin. So this work obtained, maximum work, this is called as available energy, also known as exergy, which will be equal to the thermal efficiency of the Carnot heat engine into heat supplied. Okay, that is 1 minus 25 plus 273. Carnot engine, a reversible heat engine only can give us maximum useful work. That is, heat supplied will be 4000. Answer is 2916 kilowatts. Please note that you are able to get the maximum work only when the heat engine is operating in a reversible cycle, that is a Carnot cycle. A source is there, it is supplying some heat. When can you expect the maximum work output? Only when the reversible heat engine is operating between the source and the lowest possible temperature. You can reject the heat will be the environment temperature. The lowest possible temperature you may attain for any sink will be that of the environment. So, in the concept of available energy, the environment plays a very significant role. The concept of available energy will be understood only if you know that the role of environment represented by T naught. T naught is that symbol given for the environment. Similarly, there is a concept called irreversibility. To calculate irreversibility, again the role of the environment is there. T naught into delta S of the thermodynamic universe. This is a formula for calculating irreversibility. Irreversibility is a product of the ambient temperature in Kelvin and the entropy generated in the universe during the process. Delta S change in entropy of the thermodynamic universe. Universe means system plus surroundings. Both we have to consider. So T naught into delta S is the formula for the irreversibility during a process. So answer is 2916 kilowatts. A reversible heat engine is operating between the furnace at 1100 and the lowest possible temperature, that is T naught will be the, T naught is the symbol mentioned for the environment temperature, remember that in Kelvin. In a system, if the heat energy gets absorbed, the temperature keeps on increasing. Therefore, Earth will radiate 100% energy away. It receives heat from the sun because otherwise the Earth will get heated up. Then which of the following is correct? See, Earth is there, is receiving the heat from the sun. And then why the temperature, if all that energy got absorbed, then definitely the temperature of the Earth will be increasing. No? Forever it would have reached the infinite temperatures long ago because it keeps receiving heat from the sun. Earth is receiving the heat from the sun, at the same time it is re-radiating the energy into the space. But the temperature of the sun being much lesser, the temperature of the Earth being much lesser than that of the sun, the energy is radiated from the Earth into the space, re-radiated into the space at a longer wavelength. It receives the heat from the sun at a short wavelength. Whatever the wavelengths what we are receiving, solar radiation, no? That is a short wavelength radiation, somewhere between 0.3, 0.5. Most of the solar radiation what we are receiving in the 0.3, 0.7 in that range, 0.1 in that range wavelength. But by virtue of the temperature of the Earth, it also re-radiates into the outer space. So that will be the long wavelength radiation, but Earth will be receiving energy at a low entropy energy, clustered energy or a clubbed energy. Earth is rejecting at a high entropy energy, disorderly energy, long wavelength energy into the outer space. Okay, it will get heated up. Then which of the answer will be C and as well as the D? See, this is the Earth, this is the sun, right? This is the atmosphere. The energy what we are receiving here is a short wavelength radiation, clubbed energy, short wavelength radiation. At the same time, Earth also re-radiates, re-radiation of Earth. That will be a long wavelength, long wavelength re-radiation. The carbon dioxide present in the atmosphere will be preventing this long wavelength re-radiation. That is why energy being accumulated. That is why it is also famously known as greenhouse gas. Carbon dioxide, why it is called greenhouse gas? Because it is causing a phenomenon called global warming. The levels in carbon dioxide levels increasing means it is preventing this long wavelength re-radiation, causing the global warming, causing the temperature of the Earth slowly increasing as the CO2 levels are increasing. So that is why the environmentalists will be very much warning us against the excessive levels of carbon dioxide, and there are some other greenhouse gases also, methane, etc. also. So all these greenhouse gases like carbon dioxide will prevent the re-radiation of the long wavelength re-radiation. So answer is, it is receiving low entropy energy, Earth is rejecting high entropy energy. Answer is both C and D. It is MSQ, multiple choice questions. In the GATE there are MSQ are there, okay, but the number of questions asked in the MSQ are very low. Maximum you will get 1 or 2 only in every GATE paper. So I have discussed the thermodynamics also. Any doubts if you are asking, we have the WhatsApp group. This is Sekhar from M Sigma Gokulam, which have discussed the heat transfer and thermodynamics. In future days also I will be coming with solutions of many more papers like connecting to fluid mechanics, power plant, etc. This is Sekhar from M Sigma Gokulam. Thanks for listening to this video. Good night.